Okay, I'm recording, so brief warning, I'm a bit tired today, also because it's an hour later than expected it would be, but it should be fine. So yeah, today we're talking about Poisson field generative models, which is yet another generative model based on physics, and it's a bit more complicated than last time, but we'll go step by step through it. Okay, I have to bring my mouse back in. So to give a brief summary, I'll spend a lot of time on the Poisson equation, and so the whole physical process that the paper is based on. But then from the physics to the final model, there's quite a few steps that need to be added. So we also go through them step by steps, and then we'll talk about the results they share, which are quite interesting. And then because PFGM, they later improved it with PFGM++, I'll briefly mention about some interesting things about PFGM++, but I won't give a detailed explanation because one paper is enough. So yeah, so the Poisson equation is yet another PDE involving the Laplacian as last time, where we take some source density, so which is a function from Rn to R, and okay, assume that the function is sufficiently nice. For example, it's continuous and differentiable. Here, an important assumption is that it has a compact support, and compact support here means that outside of some bounded set, rho has to be 0. So the set where the source density is non-zero is bounded, and this is an important assumption. In practice, so rho we will assume is our data distribution, and if it's an empirical, it will always be bounded, so that is not an issue. And so the rough equation is so delta, or the Laplacian, times phi, which is our unknown field, is equal to minus rho. So as mentioned, delta is again the Laplacian operator. Note that I'm differing from the paper where they used the nabla squared for the Laplacian. I'm more used to this notation, and so I use this one, but pick whichever you prefer. If we take the gradient of our solution field phi, so phi is a scalar field, and if we take its gradient, that becomes a vector field, and this satisfies what's called Gauss's law in physics, which is simply the divergence of E is equal to rho. Now, this is one of the most basic PDEs in PDE theory, but also in physics, and depending on what rho looks like and how you interpret it, you get stuff like Newtonian gravity and electrostatic theory. So this equation sort of produces a lot of basic physics, and in particular the paper takes inspiration from electrostatic theory, where we take our data distribution and interpret it as some kind of charge distribution on some plane, or at least some charge distribution in some space. Now, this equation has an analytical solution given by what's called the green function. A quick mention that the Laplacian operator here is linear, so it's a linear operator acting on some function to another function, and so at some high level, this is just a linear equation. So, like you could say, it's just a matrix times a vector equals vector, although here it's in infinite dimension, so it's a bit more complicated. So, this is just a linear equation, and so you could imagine, okay, if I have some idea of what the inverse of delta looks like, then I can find a solution, and this is sort of what we are doing here, although the Laplacian is technically not invertible. But we can still find some solution using this so-called Green's function that tells us that phi is simply the integral over, so here I'm assuming integrating over the whole space, but remember that because rho has a compact support. Really, I only need to integrate over the support. And so I integrate gxy times rho y dy. And this expression, if you turn it into a sum, it looks like a matrix times vector. So it checks out. And in the case of the Poisson equation, the green function, so green function is a general technique in PDE theory, but for the Poisson equation, it looks like in terms of this, G looks like this, where you have 1 over n minus 2 times a constant, which is the volume of a hypersphere in n minus 1 dimension. This is just a geometric constant, and there is a formula for it, but it's not super important, times 1 over the norm of x minus y to the power of n minus 2. And as an intuition, the Green's function is it's the solution for a single point source. So if you take a rho being just a single charge at a single point, this is what you would get. And notice that essentially this is a function that decreases exponentially, or at least in a power law, around y. So if you take y to be the source, for example. So essentially you get infinity at your source, and then it decays very fast as you get further from it. Similarly, you can find the expression for the Poisson field, just the integral of the gradient of g, and the gradient of g then is similarly just 1 over our constant times x minus y times over the norm of x minus y to the power of n. As an example, if you take n, our dimension, to be 3, you recover the general form of, for example, Newton's law or the Coulomb's law if you're using electricity. So that's for physical intuition. The nice thing is that, okay, we have now a vector field E, and so we can ask, okay, what happens if I take a particle and follow the vector field? And so let's do just that. So take dx over dt equals the vector field E evaluated x. And similarly, we can also imagine, okay, what happens for not just one particle, but the distribution of particles, and we can also find a similar equation. And the nice thing is that this basically tells us that we are following the field lines in some way around the distribution. So the gradient flow is what we're going to base the forge process on, but with quite a few steps involved. So as an illustration, but don't take this too seriously. Like, this is an illustration of the electric field lines. So these are the direction of the Poisson field that are around two positive charges. Note that in general, at least the paper, they assume, okay, the data just has positive charges, and so this is what it looks like. And you can see it looks a bit complicated, but the nice thing is that as you get further and further away from these sources, really it just looks like, from very far away, these two sources, they just look like one single source, and so you get something that looks spherically symmetric as you get further away, and that's something that the paper uses. Another really nice thing which the paper uses a lot is that this gradient flow, it's stiff, so it's generally not nice to solve using numerical methods, but we can rescale it. And so if we take any function f which is differentiable and continuously so, and it's strictly positive, then multiplying the gradient field E by f and plus or minus, so we're just scaling the vector field by a positive amount, or at least the amount we're scaling is always the same thing. Well, this equation will always follow this exact same trajectories as the original gradient flow, just at a different speed. So this is nice because we can escape a lot of these issues with the C4Ds, where close to the sources we're going really fast and that further away we go really slow. So this is something that the paper uses and abuses quite a lot. So to get a first figure from the paper, this is the illustration they gave of the forward process. So you have this heart-shaped distribution on the plane here, and you can see that under the dynamics they sort of get mapped outwards to this expanding sphere. And so really that's the thing that the paper relies on, that as you get further and further away, this complicated distribution near the source just becomes a uniform distribution on a sphere that goes very large. So, and similarly for a single particle, we get a similar effect. Now, this is the physics part. Unfortunately, we do need to add quite a few steps to get a workable model for this. So I'll go into them into detail, but first we need to add an extra dimension. This is because if we don't add one, we get some problems with mode collapse, and so adding an extra dimension lets us avoid that. Next, because the field is very is ill-behaved because it has all these very high and very small scales, we need to normalize it. Actually, we'll normalize it twice, and this will help in numerical stability. And then we'll actually replace the time variable with z. So the z variable, which we just added as an extra dimension, it will serve as the variable for our backward ODE, and we'll see why. So why do we need to add an extra dimension? They give a simple example of, okay, let's imagine that our distribution is just on a plane and just this disk, and let's not add any dimension and solve the Poisson field. The problem in this case is that anywhere you might start, you'll always collapse to the center. And so they say, okay, this is an example of mode collapse because what you like is being able to sample from this disk, but you can only sample from the central point. And so the solution is to add another dimension, and then following the field lines in this dimension, you actually get to sample points all across the disk. And so this is what you want. This is why you add this. You add this extra dimension. Then the thing is that, okay, notice that we're now in a 3D space. We will say, okay, then it should be a sphere, that we should start from a sphere and around around our distribution and go back to it. But in practice, because we're only interested into say landing on this plane, we can just only care about like half of the sphere, and so that's something that the paper does and don't necessarily explain that, because we only need to care about landing on a single plane, we can actually just start from one half of the sphere. So that's why we only look at a hemisphere, and they have a sort of short proof, but which it's not super insightful about why when you start from a uniform distribution on this infinitely sized sphere, the distribution when you hit the plane is exactly the distribution you started with. So yeah, this is just sort of the written thing that I just mentioned. That's okay, we add our dimension and then our original data, because of course we don't have the exact distribution, we'll have to estimate it from data. We'll just embed it with x, so x being our n dimension vector, and just add a 0 to it. No big deal. And again, the asymptotics thing that I mentioned, it's really the best intuition I found for this is that as you get further and further away, because it has bounded support, that's the important part. If it's not bounded, it could go like infinitely far, and so then it would not work. As you get further and further from it, this complicated distribution, it just looks more like just a point, and so the vector field becomes spherically symmetric. And so that's sort of the intuition why you get a uniform distribution on a sphere. Now, let's suppose we have an actual data set, so x of xi's. We'll define the empirical Poisson process as e hat. We'll note that I have my x here, and x tilde means my data points that I've augmented with this additional dimension. And so my e hat is just essentially the empirical mean of the Poisson field. So I'm just evaluating x minus xi over x minus xi to the n plus 1. So it's just basically I'm taking all of the individual sort of Poisson source for for the like treating them as just single sources, and then this term here is just normalizing it. And so you can say, okay, if you remove the normalization and add 1 over n, this is just, okay, the empirical mean of the, it basically approximating the integral over here, but with an empirical mean. And so this is why you're taking this sum, and it works in practice. Although I think the paper does give a proof of why exactly. So we take our sum, we normalize it, and actually we do even more normalization, because we multiply that square root of n and divide by none, and then usually we add, at least the paper adds, some small constant gamma to avoid dividing by 0. And note that all of these operations, because our vector field is rescalable, these don't change the actual trajectory. So the trajectory stay the same, it's just the speed at which we go through them. And so the actual vector field that's going to be approximated with with a neural network is this negative normalized field v of x tilde. And as a notation, so because this depends on some data set, we'll note that if I have some batch of data b, and I'll use the underscore or subscript p to denote that my vector fields here are calculated with respect to a given batch. So that's how we get the, at least that's how we estimate the vector field. But to get training data, we don't want to start straight from our plane, so we take some training data point x in Rn, add noise to x tilde to obtain some yz, and the way to do that, remember, we're assuming that we are within some hemisphere, and so the goal here is to sample points within that hemisphere. And to do that, so you sample y and z, and y is given by x plus some noise, where we have a term that we have a few things. So we have these epsilon x and epsilon z terms. Those are just normal, so they just come from a Gaussian distribution with hyperparameter sigma. We have this 1 plus tau to the power of m term, I'll go back to it, plus this u term, which is just uniformly sampled on the sphere. And so the idea is that you take like your initial data point, you take some point on your sphere that you want to point to, and then you add some Gaussian noise, and then this 1 plus tau term, tau I assume is greater than 0, and so because m is another random variable, it's basically selecting the sort of how close it's a control on the radius. And the idea is that by using this choice, I get more points closer to the center, or to the center of the hemisphere. And the reasoning that the paper gives is that we usually care more about the points closer to our actual distribution, whereas the points further aren't as important. So we don't need to have an exact sampling of the vector field in these regions. So similarly for EZ, it's just some Gaussian noise times this scaling parameter. And so using this, we get some points in our hemisphere that are a bit closer to the center than if we were sampling by uniform. Okay, we know how to estimate the field, we know how to get training samples. So to compute the loss, we take a mini batch B that will evaluate the vector field on, and some, we take this B to get training samples, and we take also a larger batch for estimating the normalized field, and we train a neural network f theta to minimize this loss, which is simply the mean square deviation between the f theta and our actual vector field. So no need to go through probabilistic argument. It's just we have a vector field, and we approximate it in the least squared sense. Note that I'll go back to this in later, but even though the objective is simple, evaluating this field here is a bit complicated. We'll see why. So I have the all algorithm from the paper. It's basically exactly the same that as I mentioned, so it's not super. I don't think I need to go over this in great detail. It's just the same that I just explained. Now we can finally get to the backward ODE. So the first step is that instead of solving the backward ODE in time, because first of all, okay, we know that it should be like uniformly distributed on some sphere, but we don't exactly know what time it will reach that sphere. So instead, let's actually solve the ODE respect to z. So z changes there, and so we know that we can just stop when z hits 0. And then this is just a simple chain rule application, and so we get so v underscore x is just the x component of the vector field, and z is the z component. So we take the x component divided by z, and z is just moves at constant time. And so to start evaluating, we take some z from beneath some z max, which is another hyperparameter, and we know that we should then end at z equals 0, which is our data hyperplane. But then we do another thing. So the reason to allow processing batches. So remember that this is an ODE, so we'd like to sample these ODEs in batches. And the problem is that most ODE solvers only allow you to start your ODEs from the same time step. And so to alleviate that, they map the prior on the hypersphere. So you have your points, like you have this hemisphere r equals z max. You have your point on there that should map somewhere on z equals 0, and you just project them on the hyperplane z equals z max, and this changes the prior, and so we have an exact form for that prior. But in practice, we can just sample on the hemisphere and then project. That's easier. So at the end, we just solve already with respect to z. So we start on this hyperplane and like follow the field lines to eventually hit z equals 0, or at least close to it. But that's not over, because the author decided this was still a bit slow, so they added a new time variable such that dz equals z dt. And what this means now is that z equals like e to the t star t prime, and so it's exponential, and so we solve the backward ODE. Z converges exponentially towards 0 instead of just linearly, and so it converges faster, and actually it makes the ODE, so solving the ODEs faster. So this is the final step. So yeah, we made it. So as you can see, there were quite a few hoops to go through to reach the final process, but now we can actually get to the results. So the author so they compare to DDPM. So for all their models, they use the DDPM plus or DDPM plus deep backbone for the neural network, and they compare to a bunch of models, so Stargan and so on. And what they observe is that they claim to have the best inception and FID scores, at least for normalizing flows, and that it's also faster. And here, faster means they look at the number of function evaluations for the ODE solve. And okay, it might seem that it's not a great comparison, but at least if they're using the same backbone, a function, because the same network architecture for a given a given function evaluation is about the same, so it makes sense to compare the number of function evaluations. And so you see that it works, like at least it's very much on the lower end for these. Yeah. So summary, that they achieve best inception and FID scores among normalizing flow models, and they're around 10 to 20 times faster than the SDE models with similar architectures. So pretty impressive claims. I'm sure people with more hands-on experience will be able to comment more. Another nice thing they have that so in most of their experiments they use like the standard ODE solver, which is RK45, but you could use even the simpler Euler method, which is usually not a great ODE solver, but here you can take the Euler method and like take a very large step size, and they see that the performance in terms of accuracy like performs pretty gracefully. Well, at least comparably to DDIM. So the interesting thing is this curve here where they lower the number of function evaluations by increasing the Euler step size, and we see that basically the PFGM and DDIM say they're around the same, and actually PFGM is a bit better than DDIM for most of the time, whereas the variance preserving ODE on the other hand, for very low or at least very high Euler steps, it quickly degrades. So that's a nice thing. You can like use the simplest ODE solver with very large step size, and that works pretty nice. Some miscellaneous, so this is just a boring slide, but we can look at the actual paper instead. So they mentioned that it's easy to evaluate the likelihood and to directly manipulate the latent. Well, we'll discuss that more. There are some limitations. So I think the biggest limitation is the way the training works. Is that first of all, the mini batch normalized field estimator they use, it's biased, so it's not quite accurate. And you also need a large training batch to compensate that. So this means that the evaluating this actual Poisson field is quite expensive during training. But luckily, all of these problems, like most of these problems, are fixed in the next paper, PFGM++. And to give you a very brief rundown of this paper, they generalize to adding D dimensions. And the nice thing that they show that when D goes to infinity, this is actually equivalent to diffusion models. So one nice thing. They fixed the problem with this biased estimator of the normalized field. And okay, you might say, you're adding dimensions. That means you have a larger ODE, but actually you don't need to. In practice, you add one dimension and just D intervenes in the equations, but no longer in the actual size of your problem, and so it's still just as efficient. And then they show that you can transfer, so because it's at the infinite size, it's equivalent to diffusion models, you can take hyperparameters from diffusion models and transfer them for finite D. And so pretty spiffy. So yeah, that's the end of my slides, but I have the GitHub open here, and I have both papers if we want to discuss them. So questions away.
Okay. Yeah, I guess, there's some questions in the chat, I think.
Yeah, I see. So rho is a function, so it applies on top of the data. So rho here is supposed to represent your data distribution. So assume that you're trying to approximate some probability distribution, which is you only have samples from your data. So rho here would be say your data comes from a data distribution or from a probability distribution. Rho is your probability distribution. Okay. X tilde is noise. Okay. Is the second question also solved or not?
So I guess if you go back to the slides, which maybe around 10 or 12, some number like that, where you had those. Right. So in this one, you have X tilde, which is different from the noise in the next slide, right? It was the same symbol used.
Yeah, so X is your original data, X tilde is your data plus the extra dimension. think, yeah, I probably haven't been super. Yeah, so x tilde is just x, your original data point, plus some z, and by default it's
Okay.
just x0. And yeah, so tilde just means it's the augmented data, and later on, when you add noise, you get some yz, which is your x plus the noise and the z plus the noise. Or z here is just
Yep.
d noise. So, yeah.
Thank you. Yep.
So you have x, and then you have, but it's actually the point. The point x is that in the x? What is? I guess it's confusing because you have x, the point x, which is actually embedded in xy. Is that right?
So, okay, I'm trying to make this more clear. So, I also, to respond to Jimny's comment, so we're only adding noise for the training samples, because you don't want to start from the zero plane to train. You want to sample from the hemisphere. So, because like the reason you can imagine, let's just assume that my hemisphere is centered at zero, but that might not be the case. Your distribution might be centered around something else. And so by taking a data point and disturbing it, you ensure that you're sampling a point in the hemisphere around your distribution. So that's why this noise procedure takes a data point. So x here is a data point from our training data set, and we're taking adding noise to it to get a point from the hemisphere around it. But you have, so the paper has a more clear orientation because they have different fonts for x, which I don't have. I don't think I have for my slide program. So that adds a bit of confusion. But x without anything is a data point. X tilde is a data point embedded with this additional dimension. And I think in the other things, I tend to use x indiscriminately for just the variable. Yeah, here's just a data point, but I think in other cases, in this case it might be less clear what z means.
Okay, because x as a data point, but that's in the xy plane.
Yeah.
Okay, so there's two x's. There's one, the x as the data point, and then there's the x as the.
So sorry, no. X here always means the point on the plane. So x is always a vector. It's just that for illustration purposes, it's easier to imagine a plane, but really this plane could be an arbitrary n-dimensional space. So you just have like x, which is the vector component on this space, and z, which is just along a single dimension.
And what about y?
So y, so here assume that like x and y aren't here, just x within the plane. Then the y pops up as just a temporary variable for the, like in this case y would be the x plus the noise, but it's still in the plane. So x and y are still vectors in the y is still in the plane. Or is it?
I guess if x is in Rn, y is also in Rn, but it's just some noise added to it.
Yeah. So okay. So it's still in the original data space.
Oh, so y. Oh, okay. So y is actually the x with noise added.
No. Y is x with noise added, but in the original picture that Genetics 8 showed, that x and y basically n is 2 in that case, is R2.
Yes.
So those are 2 dimensions.
Okay, that makes more sense. Okay, that the notation was confusing there. Okay.
Yeah, but generally forget about these labels here. They should be something else than x and y. But yeah, x just means the in the original data space, and Z is the what we're adding.
Okay. Okay. That
So
makes
yeah,
sense.
implicitly when I
Um,
have like these y tilde, I'm assuming I'm taking these x's, augmenting them, adding noise, and that gives me the y tilde.
okay. So y tilde is so the tilde means you have the extra dimension, and the
Yeah,
y means that you've added noise.
yeah.
Okay. Okay. Um. Yeah, I guess. Yeah, of course, I'm not very familiar with this sort of electrostatics, electrodynamics. So this, the Green's function and those sorts of things, I'm not as familiar with them. Um.
I mean, I'm not sure how useful I mean, you could argue that the intuition of following the field lines that like because you're taking this physical assumption that you have this well-defined vector field that defines your trajectories, and also the nothing that is invertible. So whereas for diffusion or IHDM, the forward process is typically not invertible by default. Here it is,
Mm-hmm,
so you just have to solve the backward ODE.
mm-hmm.
But like, I think with all the steps added, the physical intuition makes less and less sense. So I wouldn't be too attached to thinking about the like actual electric field here.
Mm-hmm. Okay. So is it kind of still like it's kind of like these it's still like a maybe like a flow, one of these sort of flow matching models or something. Maybe there's maybe some similarity there.
Um, Probably, although
You're starting out with this sort of uniform, I guess. You have some sort of uniform distribution. I guess yeah, you have this sort of uniform distribution, and you try to you try to figure out how that uniform distribution is transformed into your data distribution, and your loss is again just kind of looking at your, I guess your um yeah, looking at I guess the loss is kind of, yeah, it's comparing. V is like, what is it, the
so
that it's a
V is
vector
like
field
if
that
you look at these like field lines, you can imagine okay, I follow the curve and I have a vector that tells me where to go to follow the curve. That's the vector
yes,
field,
yes.
and we're basically approximating that vector field, but rescaled so that the like near the data distribution because it's 1 over x to the n that would blow up. So we rescale it so that it's nice near the data distribution, and as we get away,
Hmm.
because it's 1 over xn, it should like by default be very very small. So we also normalize it so that it's like it's goes at a reasonable speed everywhere. But otherwise, it's still the same vector field, just rescaled a bit.
Hmm.
And the idea is that we have this process that sort of moves our data point, these near data points along this field line. So each one has this nice little curve, and so we can just follow the lines on the in the other way to get the like to reach the initial distribution.
Yeah, so yeah, it feels like, yeah, because similarly in the flow matching model, you have these sorts of flows that try to map from one distribution to another. You follow it to map from one distribution to another, and then you have to learn how to. Yeah, I feel like there's probably some close similarity there, I think.
I mean, my impression was that
See,
sorry was
yeah, this is Dave. Uh, I think in one of your slides you did mention about equivalence to normalizing flows, right? Like maybe in 16 or so.
I mentioned that in the benchmarks or in the metrics they show that they are they have the best inception and equal among normalizing flow models. So as you could say this is a normalizing flow because you fix the flow and you just move your
Hmm.
from one distribution to your data distribution. But
Hmm.
like my impression which is arguably not super accurate from the like flow matching papers was that it's more okay, you have your target distribution and some easier distribution, and you're trying to find a flow that maps from one to the other. Whereas here the flow is fixed by your data distribution. And it just so happens that because you know that the the flow gives you a nice well-defined distribution that you can sample easily, that you don't need to like the flow is fixed, and it also fixes like a nice prior that you can sample from, and so all you need to do is just sample from the prior and solve the equation.
But you still the flow is fixed. So in the loss function, let me go back to the loss function.
I think it's there.
You have okay, so you have VBL. So that is your flow.
Yeah.
And it's so you're trying to learn the flow because you have F theta. So your model's trying to learn the flow. It's not like it's it isn't. Yeah, I don't think it's fixed flow, is it?
So the actual flow here, it is fixed by your data distribution, right? So it's the like the data distribution here fixes a flow, and that's the flow you're trying to learn. So modulo the fact that you have to approximate by large batches and that there's some bias there, the actual vector field that you're trying to learn is fixed by your data distribution.
Mm-hmm.
So you're just trying to approximate some vector field.
Or in that case, by the batch distribution, the batch data.
Yeah.
We're learning for each batch at a time, and then, yeah.
So how was VBL determined then? How exactly is it determined again?
So VBL, so remember that with like here, imagine that D is just BL.
Okay.
So like imagine that so X tilde is one of my training data points, and Xi is from my BL data point. So I'm taking this sum and then normalizing it. And so like you really do need these two batches, one from to get your training data and one to get your field estimator. And so then you can always further.
And what's the need for this negative normalized field?
So they mentioned that they want to avoid fluctuations in this norm here. So even though this is already more or less normalized, like technically there's still, I think it's not quite, this thing is not quite normalized, but almost. But this is normalized because you're dividing by norm except for this square root of n. But at least.
But why is it negative though? I guess then.
I've
changed the complete sign of it, I guess.
I think the sign doesn't matter a lot here, but yeah, I don't think they maybe they do, but I don't think they give a like explanation why you want to take a negative sign. I think you could take the positive and just change it somewhere else, and it wouldn't matter. I think it's just that because your at the end of the day you want backward process, you want to go the other way, so the reverse of the is just like take the vector field and multiply by -1 to go the other way. And so by having this step, when you learn f is just the vector field that points toward your data distribution.
Okay, so yeah, Molly saying that the blog post had some more information about the blog post talked about
Yeah, yeah. I had it open on my other browser. Forgot here.
check here.
I think actually there's the link on the Discord, so I'll open it. Yeah, actually the blog post was pretty nice.
What's this in? Fiction, flow model interpretation. Oh, okay. For those interested, you can cast a flow model directly with the probability density.
So yeah, this is a nice illustration of my point about the like complicated distribution giving a complicated field close to it, and as you get further away, it looks like just a source. So it simplifies.
So yeah, one question I do have. This is supposed to be deterministic, right? So okay, but it's any point. Okay, never mind. I was just trying to see. I guess there's no way to make this stochastic, is there?
As in to get an SD.
Yeah.
Presumably not.
There's any sort of stochastic interpretation of this.
At least they don't give one. I mean, you do have some stochasticity in the way that you approximate the Poisson field from your data distribution, and like you get some amount of noise. But yeah, presumably it's not something that's purely that can be. I mean, maybe I think probably you can like give a stochastic augmentation for this, but I don't know enough about it. Yeah, I'm trying to look at the. Yeah, generally the blog post is pretty nice because there's a lot of details. I should actually have read it a second time before making the slides.
So during training with that noise added, how does that impact the learning? Is that separated from the that injection is kind of reparameterization in some sense?
You mean the noise to make the training samples, or the noise when choosing your vector field approximation batch?
So, so for the noise for the training sample, that's just the noise added, but at the end of the day, that has to match to the original distribution, right? So that is probably just accounting for some variation in your data distribution that you may not have accounted for. I'm assuming, is that right? That your data set doesn't have. So in case you get something like, it allows you to generate something which is nearby as well.
I think the way you get that is that when you solve the backward process, you stop when you reach the z equals 0, and so when you reach z equals 0, you may or may not land at where there was a data point. So in that sense, your z equals 0 sort of approximates the gives you something that was not in your original data set, but I'm not super clear on whether that would translate to some generally new images. But yeah, I'm afraid I'm not
Not
familiar enough.
new, well, maybe newer images, but from the same domain, if you may. Like some way, which it has never seen before. Because if it's going to generate the same images that it has seen, then of course it's not useful, if you may. Right. So that's why
Yeah.
this noise injection will help you uh, get that generalization for the domain that it has trained this electrostatic uh, uh, flow for. What was the other noise you said? So I'm just thinking if noise can be an issue for the
Yeah, I'm afraid I
that
don't
particular.
have a clear answer because, like I mentioned last time, I'm mostly into the math and less into the practical machine learning. So I don't know enough to answer that. I think yeah, they do mention maybe that gives you a bit of an answer that because you have some latent involved, you can do stuff with latent and get some modifications. So I think that might be some evidence that, for example, we can interpolate. So that would be some evidence that you get some something that
So
like
variation, yeah.
yeah.
So how is it? How are images? Um, how you get the latent representation of an image? How does that work?
So I'm
Do
guessing
you
the
just
latent representation is when like when you take your starting point from the for the for the backward process, like you sample on this hyperplane.
Mhm.
I think that's your latent.
Yeah, but I guess give it an image. Like, do you just I guess you just like
Huh.
solve the ODE in reverse or something like this, or like yeah.
I
So you
think
have an
yeah, I think
image,
that
then
that's a bit degenerate in this case. If you have like an exact image from your dataset, it's on the plane, so like on the zero plane. So the latent would be like at infinity. So I think that's one case where it's maybe less well defined. But
oh okay.
but if you interpret it as instead of the plane, you interpret it as like the hemisphere, that would be on the edge of the hemisphere. But then I think you'd still
Yeah.
have some trouble with data points being on mapped to the same latent.
Hmm. Why do you think there'll be problems mapping it to the same mapping to the same latent?
So let me try and find of course I'm assuming that by latent they mean the point on like on the sampling plane.
Mm-hmm.
So let's go back to the schematic they had sometime later. Um, yeah, so let's assume that the latent is like points on this hemisphere. Then for any point like within the hemisphere, I can just like project from, or at least follow follow the flow to the hemisphere and land there.
Mm-hmm.
Okay, no, then forget what I said. I think you can do the same just from your data point. You take your data point on the z equals 0 plane and you follow the forward process back to the hemisphere.
Would it be the forward process, or would we be solving the ODE like
So the
reverse?
solving
Because
the ODE
the forward
inverse,
process keeps adding noise, right? The forward process is adding noise.
there's no noise in the process. I don't think. Like
So I guess forward process is what you mean, like during trading, or what do you mean by forward process? Because the trading forward process adds noise, right?
it add noise to generate training data points to like it estimates this vector field.
Oh, I see what you mean. Okay, but then So when you say forward process, you just mean solving the ODE in reverse, then, right?
No, the forward process is like
So I think
this.
forward.
Forward process is like mapping from your data distribution to the hemisphere. Backward is from the hemisphere to the plane.
So how do you map
So
from the data distribution for the hemisphere? You have to solve the ODE, right?
Yeah, through the forward process. So maybe you take your
Okay.
data point
is
at
that
a small
the
z. Sorry.
sorry? May I ask? Is that in the loss function where you have that new b? That's the forward, right? And then no, that's still the reverse in the loss function where you have the new for the batch.
So the loss function, like the loss function, is all about approximating the vector field. So you have
Right.
like the forward process is an ODE, which is given by a vector field, and you're trying to approximate that vector field. And to
Right.
approximate your
Right.
vector field, you have some randomness involved because you're sampling that data points and you're sampling points on the within the hemisphere or like within the ball to approximate the whole vector field within the hemisphere. So there is some noise in that you don't get like exactly the vector field, but almost.
Okay.
But then
Okay.
both processes are just ODEs that are deterministic.
Right. Okay. So if you have more points, yeah, that leads to a better estimate of your field. So that's why then you have to start with a larger batch for the estimation of the field and learn. So like if you wanted to, you could just if you had like if you just had like a lot of like I guess memory and you just had a lot of points, you could just kind of calculate out the vector field automatically, and then you would need to learn a model, right?
Yeah, but then you need to carry all these data points every time you want to sample from the model. So.
Right, right. But theoretically, it's possible.
Yeah, I mean, it's basically like a KNN at this point, almost.
Hmm. Okay. I see what you mean. Okay.
But even then, like sampling, it's quite expensive. At least I did some. I tried to get like a nice image of showing that the near the distribution, the vector field is quite complicated. It was a
Mm-hmm.
bit expensive, although it's probably because I wasn't doing it super efficiently. But like the fact that you're taking one over something, even if you're normalizing it numerically,
Mm-hmm.
that can cause some trouble, and that's why they had to go through the pain of like normalizing the vector field and doing this and that.
Mm-hmm. Okay.
Can this process be guided?
That's a good question. Yeah.
Yeah, I don't think this one can. At least they don't. The paper doesn't mention it, but the if you look even at the GitHub for the project, they mentioned that okay, we now recommend the PFGM because you can do okay, conditional generation, more efficient training. So probably the thing to look at for that question would be PFGM instead. But I'd assume if you wanted to guide it, like one thing is that because it's just an
If you want to
ODE.
guide it somehow, you have to somehow adapt the vector field somehow to
Yeah,
account for that whatever you're trying to guide
which might
with the
be
with the
by
with the,
I think maybe if you go back to the like physical intuition that you have a like a charge density, maybe you can like add some term that gives more weight or more charge to the like data points from the class you care about in some way. So you're like scaling your charge distribution by to give more weight to the places you care about.
I wonder if you could use since we're using the physics analogy already, this is similar to like an electrodynamics simulation, some kind of an external force, like a different charge distribution outside of the one we're using for sampling, as something analogous to guiding. I'm just trying to think off the top of my head, but I think there's a huge, rich field of literature in the physics literature from decades back that I think would be able to mine if this actually is practical.
Yeah.
Yeah, I think now that I remember, I think the end of the paper here they mentioned some future work, and they mention a few things. Sorry, I think it's just conclusion. Nope. Wait. Limitations. I think that's at the end actually. Limitations and future directions. So several potential improvements. First, they mentioned that they have a bias estimator, so that's a problem. So some potential direction incorporating more physical tools, so we can exploit renormalization to make the Poisson field well behaved in near field. So yeah, renormalization is an entire kind of word, but it's a fairly widely used technique in physics. And I think maybe to go back to your question about like making it an SDE, they mentioned another possibility to place a point charge of a quantum particle whose position uncertainty fills the empty space among nearest neighbor data samples and makes the data manifold smoother. So that would be like an example of taking the physics equation to make it stochastic.
Yeah.
So I don't think I've read the PFGM++ paper in detail to see if they did that, but yeah, presumably these guys are on the case for physics-based, at least physics-inspired machine learning.
Right. Interesting. Okay. Does anyone else have any question? I think it's the overall idea is not too complicated, but it seems like a lot of the electrostatics math kind of or electrodynamics math kind of makes it more complicated.
At least, yeah, if you try to get to the proofs, like I don't think I've even like gone through all the proofs because I figured, okay, this is a lot of math that doesn't seem to be adding like interesting intuition, so I dropped it. And yeah, I think
Math, though, sorry to interrupt, but the math for us is kind of it's a bit off-putting because we haven't seen it before. But things like Green's function, like every physics grad student is going to know that off the top of their head. So I think it opens up a lot of multidisciplinary approaches to bring a whole new, a lot of new innovations into the field from the physics world, which has.
Sure, but then when I look at these proofs here, those look to me like basically almost mechanical, like going through the motions of proving that it works. But in terms of intuition, okay, the intuition about the green function is not, but the actual mathematical reasoning here is not super insightful, I don't think. So I agree that the techniques from physics and math are useful both for the paper, but when it's just a wall of maths to justify that their approximation works, it's not
I would
super
think
palatable.
sort of more the intuition behind it as opposed to the actual mathematical machinery. I mean, my eyes glaze over when there's a lot that's pretty opaque.
Yeah, so that's why I focused on the intuition as well. yeah,
I'm just looking at some of the reviews. Apparently, they would do before they used to do some sort of slow forward ODE simulation instead of the sort of I guess they call it a simplified perturbation algorithm. So that was interesting. I guess this is a new thing that they added in the original version. This was not there. That their trading algorithm. So that's kind of interesting.
Yeah, I think just by looking at the like the complicated the motions you have to go from the basic intuition from physics to the final model, I think you can tell that they had to go through a couple of iterations on this one.
Okay, if there are no other questions, I guess maybe if people are interested, we could think about covering the PFGM plus plus at one point as well. Um, I don't know. It may also be pretty intense as on the math side, especially. So I don't know. It's up, I guess if you guys are interested, we can cover it. Otherwise, it's okay. Um, yeah. But next week, I think Molly is presenting one of the papers on one of the recent diffusion model papers. Was it Min? I forget what it's called.
Min S and R.
Right,
See.
right.
Yeah.
Okay. Yeah, so we'll talk about that next time. And then yeah, okay. Uh, thanks everyone for joining again. And of course, if you have any other questions, anything to discuss, feel free to put it in the chat as well. Yeah, I guess I'll see you all next time. And thank you again, Genetics, for your great presentation.
Yeah, if I can just like say one last thing before finish about the like learning math thing. So a few of you may have seen the math reading group that I started as a follow from the functional analysis. Like I think this reading group is a space where like we can actually learn these math or physics, especially as a way to get more intuition or tools for machine learning. So if people want to learn more math or more physics, that might be a nice place to go. And we're staying like we're looking for ideas and suggestions. So if you're interested, do check it out. Thank you very much.
Okay, so you haven't you don't have a topic yet or anything specific.
So Dashiell, not sure how to pronounce his name, but we have a potential first topic being representation theory, which is okay. You have groups and you represent them as matrices, and so if you're looking at transformers, it's all matrices. So it's an example, but yeah, we're open to ideas and suggestions for this one.
Okay, cool. That sounds very interesting. Okay, then talk to you all next week then.
Yep. See you next week.